All right, guys, so let's end this section with a couple of proofs. And the first thing we're going to prove is our power rule. So remember, when we have something like this, f of x is equal to x to the nth, the good old days, right? The derivative is equal to, bring down the exponent, and then subtract 1 for the new exponent, okay? So we're going to prove this using logarithmic differentiation. Okay, so the first thing we're going to do is, let's say we have, y equals x to the n. Remember, f is just a fancy way of saying y. We're going to take the natural log of both sides. Okay, so again, I'll write this as a proof, because we never proved it, at the beginning of this part of differentiation. All right, so now that we did that, we can move that constant n to the front. And let's go ahead and take the derivative with respect to x of both sides. Okay, so 1 over y times y prime, which we're trying to find this y prime, is equal to n, which is a constant, times 1 over x. Okay, lovely. And then to get y prime by itself, let's multiply both sides by y. And I'm just going to put the y in the numerator of the x. That's where I decided to put it. And we know that we have to make a substitution for y. Y was originally x to the n. Okay, so what happens to the exponents when we're dividing by the same base? We're subtracting. So it's going to be n minus 1. So y prime is equal to n times x to the n minus 1. And that's exactly what we were trying to show. Right? We were able to prove it really quickly using differentiation, logarithmic differentiation. All right, so one more thing in this section. We're also going to prove, we're going to show that our favorite constant e, well, pi might be our favorite constant, e comes in a close second, is equal to the following. The limit as n approaches infinity of 1 plus 1 over n raised to the nth. Okay, and we're going to show why this is true. Okay, so I'm going to put a little box around that. This is our statement, and here's our proof. Okay, so we're going to start off, and let's let a function f be equal to the natural log of x. All right, and that means the derivative of that function is 1 over x. That means the derivative at 1 is equal to 1. Okay, so just 3 little facts that we can make from that very first assumption. We're going to switch over to our derivative definition. So if f prime of 1 is equal to 1, that means the limit as h approaches 0 of f of 1 plus h minus f of 1 over h. And that's the limit definition of the derivative, okay? So I'm going to do a little bit of variable magic. A variable by any other name is the same, right? So instead of h, let's say x. I don't want your assistance. So instead of h, let's say x. And it's the same, right? X. All right, so our f function is the natural log. So let's make all those substitutions. Oops. How did you do that? And as you're writing this, what's the natural log of 1? It's 0, right? Saying e to what exponent is 1? Well, e to the 0 is equal to 1. So that means natural log of 1 is equal to 0. Okay, so let's clean up that expression. So this is going to go to 0, so it just disappears. And then I'm going to bring out the 1 over x in front. Instead of dividing by x, we can multiply it by 1 over x. And I'm doing that because now we can use a logarithm rule. Let's put that as the exponent. Okay, and now all of that, remember, let me go back up, is equal to 1. So let me rewrite that. So all of that is equal to 1. Okay, so we've done this amazing thing, and now we're trying to get a formula for E. Okay, so let's start combining some of these thoughts. So I think this calls for a rainbow. E is equal to e to the first, right? E is equal to e to the first. And 1 is just this expression. So we're going to say, I'm going to write it down here so I have room. Give me a second. Okay, so e to the first is going to be the same as e as to limit as x approaches 0. I'm having a little lag time. There it goes. Okay, so now we know when we take the limit of compositions of functions, we can take the limit of the inside function first, or we can move the limit to the outside of the whole function. That was chapter 2 stuff. Okay, so there you go. And now we've created the situation where we have our composition of inverse functions, right? E to what power is this natural logarithm? Essentially, these are going to cancel. So they're equal to, or this is equal to just 1 plus x raised to the 1 over x. Okay, and remember we started at e. So we're almost there. The last thing we're going to do is we're going to make a substitution for 1 over x. We're going to say that 1 over x is n. And if 1 over x is n, then let's rearrange this kind of a cross multiply. Then x is equal to 1 over n. Okay? And now if x is going to 0, if x is going to 0, we'll modify it. We'll go to the right. If x is going to 0 from the right, then 1 over n is going to be going to infinity, right? Positive infinity. Okay, so let's make some modifications. So now e is equal to the limit, not as 0 as x goes to 0. Now we're going to say as n goes to infinity of 1 plus 1 over n, all right, which is going to make this go to 0 to the nth power. All right, so we just made some couple substitutions right there. And that's exactly what we were trying to show. All right, and then there you go. All right, so we were able to prove that using some of our logarithm rules. And then that is that from this ginormous section.